So here's our friend, the integrated rate equation, and remember that this is only if you're second order. If you're first order, this equation's no good whatsoever. Some people like to write the t in there to go ahead and show that that's the concentration at time t. Some people say, it's obvious, there's no need to do it. I don't really know. I prefer one over the other, but it's up to you, I suppose. So how do we test for this? Well, it turns out this looks just like the equation for a straight line. If we go ahead and we write the equation for a straight line, y equals mx plus b, we can see that if we plot 1 over concentration at time t on the y-axis, and we plot time on the x-axis, then if it's second order, we should see a straight line with slope k, and the y-intercept should be 1 over the original concentration. And actually that's a test for a second order reaction. So let's go ahead and sketch out what that would look like. So we're plotting on the y-axis 1 over the concentration at time t, and on the x-axis we're plotting time. If we've got a second order reaction, then this thing is going to generate data that's going to look something like that. Okay, it's got a positive slope, so rate constants are always positive. Also, you can say, well, the concentration of A has got to be going down with time. And when you take the reciprocal, then something that's getting smaller and smaller, the reciprocal is getting bigger and bigger. So we know with time, it's going to have a positive slope. And if you look at these and you go ahead and you plot them, you can see they pretty much fall along a straight line. And so that's really a test. And so if we were plotting our data like we're going to do in lab, if you plot it and 1 over concentration with time is a straight line, this is a test for second order. Now if you had some data that looked like this when you plotted it, you can see that that is nowhere near a straight line. And so what does that tell you? That tells you that this data here, whatever the reaction order is, it ain't second order. Could be first, third, 0, some fractional order, but it certainly isn't second order. And the human brain's really good at seeing straight lines. And so this is a really nice way to tell if you've got a second order process or not. So how do we determine the half-life? And you remember the half-life is given the symbol t sub a half, and this is the time for half the reactant concentrations to be used up. And we can go ahead and we can go back to the integrated rate equation. So 1 over the concentration at time t is 1 over the original concentration plus kT. And we can go ahead and we can calculate the half-life. And so we can say, well, at t equals 0, the concentration of A, well, we'll just call that A sub 0. And at the half-life, we don't know what it is yet, but we can calculate it, then the concentration of A is 1/2 of the original value. And so we can substitute these into the expression above. So let's do that. Okay, so 1 over the concentration at the half-life, so that's 1/2 of where we started, is equal to 1 over the original concentration plus K times by our half-life. Okay, so if we find out what T sub a half is, then we'll be able to calculate our half-life. How can we do that? Well, a few steps of algebra here. First of all, we've got 1 over a half, and we know that 1 over a half is the same thing as 2 over what was on the bottom. This term here we can bring to the other side by subtraction, so that's minus 1 over a sub 0. And of course we can do that, 2 over something minus 1 over something. That's just 1 over the thing, and that's equal to k times by the half-life, which is what we're trying to solve for. And let's rearrange that equation. for the half-life, so t sub 1/2 is equal to 1 over a sub 0 times by the second order rate constant. Now notice here that unlike the first order, and if you remember for a first order half-life, okay, it's not dependent on the concentration. That is to say that it doesn't matter how much you've got, it takes the same amount of time for half of it to get used up. Now for a second order half-life, it depends on the original concentration. In fact, we can go ahead and we can say that t sub 1/2 is inversely proportional to the original concentration. That means that the more of it gets used up, the longer it takes for an additional half to get used up. And so if you look at your half-lives, they get longer and longer and longer with these guys. So for instance, maybe the first half-life takes a second. Well, the second half-life might take 2 seconds now. The third half-life, 4. The fourth half-life, 8 seconds. And so it gets longer and longer and longer. And so if we try and plot a concentration versus time graph out, then what we're going to see is something that looks like this, and it progressively gets, so this is the amount of time for half of it to decay. Once half of it's already decayed, the amount of time for another half to decay, you can see it's much, much bigger. And a third half-life, it would take, well actually it would go completely off the page. And so it just takes longer and longer and longer for half the material to decay away. So this slide's a nice summary of everything. And we've looked at the first and the second order processes. So first order has this rate law. We've looked at how to calculate the units for the rate constant. We've shown the integrated rate equation and the half-life. And here you can see the half-life. There's no mention of concentration at all. It takes the same amount of time for half the stuff to get used up. For a second order process, here's the rate law. So the power is the order. We've got an expression here, and the half-life expression depends inversely proportional upon the original concentration of A. So as we use it up, it takes longer and longer and longer for each additional half to disappear. Now if you've got a zero order reaction, which is pretty cool because a zero order, the concentration of A doesn't have any effect at all. And you can think of that as A to the 0 power. Anything to the 0, of course, is 1. So this is a reaction that takes the same speed all the way along. Unlike most reactions that start off fast and go slow, this guy just plods at the exact same speed over and over again. You can derive the integrated rate equation. It looks something like this. And actually, we should probably go ahead and see what we should plot here. So if we've got A of t, okay, equaling to minus kt plus A sub 0, then this is one where we could say if we plotted that on the y-axis and time on the x-axis, then we'd have an equation for a straight line, and the slope would be minus the rate constant, and the b, the y-intercept value here, would be the original concentration. So that would actually be a test of zero order. And so if we had some data and we plotted concentration versus time, if our data looks something like this, okay, and you can see that looks pretty linear, right? Well, that's a test for for zero order. So if we saw that, we could say, yay, it's zero order, we're done. And we could go ahead and we can measure the slope, and the slope is minus the rate constant. So we could flip the sign of the slope to calculate the value of k. Cool, huh?